So I'm excited to introduce Jesse. They're an intern at NVIDIA's Toronto AI Lab, Spatial Intelligence Lab now, and they started last May. Jesse comes with a strong background in generative methods, previously working in methods in differential geometry. Jesse also has an interesting perspective drawing parallels between some of the ideas in audio and 3D generation that we've worked on in our group. And they have an expertise in music as a unique angle to this work. So this is a really fun project. It's nicely leveraging Stable Audio Open, which came out at a nice time for us. And yeah, please take it away.
Yeah, expertise is a strong word, but I'm interested in all those things. So I'm Jesse. I'm going to introduce our project on audio score distillation sampling. That's what the SDS in the title stands for. Like Jonathan just said, this is a method that tries to kind of blend a bit of the ideas from 3D generative modeling and to take some of the successes that realized in that realm and translate them into a new domain of audio and sound. Okay, so before I give you the actual guts of this method, the TLDR, and if you take nothing else away from this talk, what I want you to remember is that the basic core idea here is that we want to distill a generative model. So we have a pre-trained generative model, and we want to use that to tune some task. We wanted to solve an audio task. So if you take nothing else away, the picture you can have in your head is that we're using a diffusion model to program a synthesizer. But audio tasks could be much more than that. So when I say audio task, really what I have in mind is some sort of task that depends on some parameters. And like I showed before, that could be some envelope or modulation parameters, or like a synthesizer, like the DX7 on the last slide. Or it could just be some material properties in a simulator, or a few other things, as we'll see later. But the core idea here is that we have some task that depends on parameters. So it's a parametric function that takes those parameters and can be rendered to produce an audio output. So again, for the synthesizer, that would consist of playing the synthesizer. If you had like an audio simulation, say a physics simulation that could simulate sound, that would consist of running the simulator and taking the output from that simulator. And yeah, one quick note on that is just that in the way this happens, we're always going to assume that's differentiably rendered. That's important to our method. We're going to need that later because we're going to use that derivative to basically propagate our update back into the parameters of the task at hand. Cool. So I will then tell you kind of the core idea, and this is going to be a big kind of slide that kind of gives you a graphical animation of how the score distillation method works in audio. But again, the core idea is really that we want to use the pre-trained diffusion model. And now I'm also telling you that we're going to have a user-specified prompt. So that prompt is going to describe what the task is trying to do, so what the output should sound like. And we're going to combine those things into an update for the parameters of the task. So what this is going to look like is something like what we just showed. We have the task and the parameters. We're going to render that to produce an audio output. But then that output is going to get fed into our Audio-SDS update. And inside this update, it's going to take not only the rendered output, but it's also going to take the output of the diffusion, or no, sorry, it's also going to take the diffusion model, and it's also going to take the prompt. And it's by taking advantage of all these three things together, it's going to generate an update direction that basically aligns the parameters better with the prompt. So the point is to use the knowledge basically contained in the diffusion model along with the conditioning of the prompt to basically update the parameters specific to the task. And what is really cool about this is even with just one diffusion model, we can apply this to a wide range of tasks. So we can reuse the same diffusion model. We don't need to retrain a different diffusion model. We don't need to retrain some sort of different deep network. We are just using some sort of pre-trained, it could be some sort of huge foundation model that's been created, trained for us, let's say. And we're now applying it to a pretty wide set of different problems. Cool. Is that good so far? Is there anything I can clarify?
So in all of those tasks, this is going to be the only update.
Yeah.
The good result of the diffusion one. No, like other losses.
Well, this is the core method. There's a small modification for the last task that I'll show you. But in essence, it's really the same thing. And that modification really comes from an additional constraint in that specific problem. But in a sense, I think that actually kind of shows how flexible this is, because you can then easily combine it with other constraints as well if you have a different problem setting. But you don't need to, and this directly applies to the synthesizer examples that we're going to see in a second. Yeah, so as someone with a math degree, I'm legally required to put a certain number of symbols in each talk. So I'm going to give you some symbols to explain what that blue box is doing. But the core idea is basically this. So this formula is what is happening in each step of this update. This USDS represents the update. And you can basically separate it into these three different components. Or not basically, you can exactly separate it. And that's that we have the X theta, which is the output. So that was the rendered output on the last slide. We have this YT. So this is a little bit more complicated to digest, but this is, I'm going to write out the full explanation in a second. But this is basically the thing that we've sort of edited with the diffusion model, if you will. It's kind of spiritually similar almost to like STE edit in a sense. And the idea there is that we've basically taken the output that we take from the current task. We've basically added some noise, and then we've partially sampled it. So conditioned on the prompt, we've used the diffusion model to basically sample, starting from the rendered output plus some noise. But we don't go, to full noise. The point is basically that you're using the diffusion model to update this output to be better aligned with the prompt. But you're not just sampling from the diffusion model itself. It's sort of like an interpolation between those things, but using the SDE or the Markov chain, of the diffusion model itself. And like I said, the last thing is the Jacobian of the rendering process. So this is basically the thing that translates this section right here. So these two things are basically audio buffers, right? So these are in audio space, but our parameters might be somewhere else. So we then need to take this difference and we need to push it or pull it back basically into the space of parameters. And maybe just to write out quickly, this is helpful. It's a lot of symbols all at once. I promise I'll show you an example in just a second. But yeah, that's basically what's happening is we're adding some noise and we're basically using the like alpha and sigma from the diffusion model itself. And we are re-sampling that YT by solving backwards in time, starting from that point in that time, which the time is also going to be sampled between 0 and 1. Yeah, that's basically a symbolic representation of what's going on. But if that's a little bit too much at once, basically, again, the idea here is that we're trying to back propagate the difference between the task output, so that would be this X theta, and the output nudged towards the diffusion models prior. So basically, it's the difference between what we have and what the diffusion model thinks we should want given that prompt. All right, it's a lot of symbols, so let's look at an example. So one of the first things we considered was tuning an impact synthesizer. Don't worry too much about what that is specifically under the hood. Again, it's kind of speaking to the generality of our method, that it's agnostic to the parameterization. But I think it's, I'll give you a few words. Basically, it's a parametric model that represents sort of like knocking sounds or banging or something like this, some sort of impact, some physical collision between two objects. And it has a bunch of parameters that are directly related to things like material properties of those objects. In a pretty simplified way, this is a toy example, but it will show kind of how this can work in practice. And In this example, we wanted the output of the synthesizer to sound more like a kick drum, some sort of bassy rumble thing. This is written in lovely prompt grammar, so it's not perfect English, but it's a good description kind of what we're looking for, the impact, the output of this impact synthesizer. So hopefully you can hear that. If people on the call hear that. It'd be great to get a yes or no. I'll just say quickly before we find out that basically, yeah, this is exactly what we saw before. So we're taking our task here, which is the impact synth, and we're just rendering it to produce the audio output. We'll find out if people can hear that. Yay, perfect. All right, exciting. So then the next thing we're going to do is we're going to do our diffusion kind of partial sample here. And that looks like that. So that took that output that probably didn't sound very much like a kick drum at all, and using the diffusion model, it's partially adding some noise and denoising, and that's the output that in this case we use stable audio open. That's essentially the output that is deemed more likely by stable audio output, if you will, in a sense. And then taking these two things, taking the difference, like I showed on the last slide, you're going to propagate that back into the parameters of the synthesizer itself, and those are then updated to better reproduce this more likely input. Is that making some sense? Any more?
Do you have a result of the diffusion model output? Not through the parametric model? Like, what is the diffusion model output given this prompt?
Oh,
How does it sound?
it sounds not so far off the thing at the end.
Because that's the baseline.
So the baseline, in what sense? Like,
Instead of going through the you need to show that it's valuable to go through this parametric part.
okay. Yeah. So I think like the value for this often is that sometimes you want a model that's maybe more interpretable. For this sort of impact synthesis, it's also easier to apply this, say, if you wanted multiple impacts or multiple collisions, right? Because those can interfere with each other in different ways that if you just, counting things is a famous example where the generative models seem to struggle a bit, right, to generate, certain specific numbers of things. So if I want to knock them over 4 times, that might be a case where that would be better. But also in general, often you want some sort of level of interpretability. So you might want to kind of be able to disentangle these parameters. So here actually it's kind of cool. I didn't show you what this looks like specifically, but if you look at the paper, you can find the formula. These like lambdas are sort of correlated to the frequency or kind of wavelength of the object, so the physical dimensions of the object that's kind of being simulated. And the D are kind of the decay parameters. So those are correlated with kind of like how elastic the material is in a sense, right? I don't want to say it's too physical, but you might be able to see how that could be valuable in different cases, right? Beyond just using the output of the model itself, right? A bit rambly. Does that kind of answer the question? Okay, cool. What's next here? Okay, so and then I'm just going to show you quickly kind of what we had at the start and what we get after training using this method. So just play the results. It's a little quiet in the room, but hopefully on the call it's a little bit louder. Yeah, it's it starts off basically being essentially just some sort of noisy output, and after running, I think we ran about 150. This is about 1,500 iterations, I think. Kind of depends on the hyperparameters and how you set everything up. Well, you can see that the output sounds. Hopefully, you can hear that the output sounds a lot more like an actual kick drum and not just a bunch of noise. Cool. Yeah, so now just to show it on a kind of different example, right? synthesizers, you know, are fun, but they're kind of toy examples. So maybe something that's more relevant to sort of real world problem would be source separation. So this specifically is, if you imagine, you know, having some audio data. So if I just take some generic audio that I, you know, go outside and record on the street, that's often going to be, you know, a mixture of different noises. So if I were to go outside, you know, here in Toronto on King Street, you might go outside on the road and you hear a bunch of people yelling, you'd hear the streetcars going by, you'd hear the birds flying overhead, right? And often you would like to separate those things. So to give you sort of a concrete example. Yeah, so that would sound like someone busking very poorly outside, you know, not, not the best saxophone playing ever, but you might be able to hear that there's actually two things going on in that audio file. So if we split that up, we've got something that sounds like this. And something that represents, you know, traffic noise. There we go. Okay, we pick at the end. Sorry, that one's a little broken, but it's supposed to just be the traffic noise that you heard right at the end of that file. But anyway, the point is that this sort of combination of sounds in this manner is a pretty natural thing that happens all the time in the world around you. And your brain kind of does this quite naturally and can kind of just take sound like this, you know, most famously, if you have, you know, the cocktail party problem, you have a bunch of people talking in a room, you quite naturally disentangle, you know, depending on the acoustics, obviously, but it's you can quite naturally disentangle different people speaking from each other, even though your brain actually just gets all the information at once, right? And so we can do this naturally, but it would be, you know, tempting to ask, is there a way we can do this automatically? And I'm here to tell you that Audio-SDS can also do this. And let's see how that can happen, right? Is it clear kind of what I'm talking about? Is there any questions? Anything? Awesome. Okay, cool. I think the core kind of thing I just wanted to point out that wasn't also in the slide is just that source separation is really cool because audio is additive. So audio is actually linear when you combine different sources. It's not like a vision. Imagine composing, you know, two pictures or something like that. If you just add them together, it's just gonna be a blurry mess. But this is actually up to, you know, some nonlinear effects and weird absorption and other things that only like acoustics nerds care about. Sound is pretty linear, so this is actually a lot more feasible than some problems. And yeah, with that out of the way, let's see how we could use Audio-SDS to actually perform this sort of source separation. So here, the user is going to supply a set of prompts. So in this example, we have 2 prompts, and then the SDS, so the Score Distillation Sampling, is really used to align those individual sources with the prompts themselves. So, well, sorry, the user is going to supply 2 prompts, and they're also going to supply the mixture of the audio that we want to separate, right? And here, the parameters, just to be crystal clear, are literally these 2 sources themselves. And so to do source separation with Audio-SDS, we're going to first combine the sources. So we're going to sum the 2 sources that we're working with to get the reconstructed mixture. So this is what the output of the task here is currently producing. And in this problem, we kind of have these 2 kind of separate constraints. So we want the sources to sound more like the prompts that are given, and we want the sources to sound more like the prompts that are given, but at the same time, we also want those sources to still pretty closely fit the mixture we've been supplied by the user, because that's the thing we're trying to decompose, right? And so in this case, we combine the Audio-SDS update with this additional constraint that we have on the solution. And we basically combine them in this way to produce this sort of composite update. So we do SDS with the prompts, and we also take the difference to the target. So the target mixture, yeah, again, is that thing there. We're going to take that difference. We're going to combine these two things. And then we're going to basically use those to update the sources themselves. So those then go back, get pushed back through the rendering function, which in this case is literally just like linearly combining these things. And we, in conjunction with those SDS updates, we are then optimizing the sources to simultaneously reconstruct the given mixture, while also better aligning with the given prompts. And I think I'll just show you an example. So the same thing as before. So the input mixed audio again is this kind of horrendous sounding mixture of a saxophone and some traffic noise. And hopefully, as you can hear, that decomposes that mixed audio reasonably well, I would say. And this is really not taking a huge number of iterations. I mean, iteration count is maybe not the best representation of computational effort because they're kind of expensive because of the sampling steps. But at a course level, this should give you an idea of kind of what's going on. We do source separation. Yeah, I would just say there's an important caveat here. It's just that I want to be crystal clear that this output we've separated is also generated with a diffusion model. So this is still like a prototype. It's still a it's a test case. That said, we do have some examples on our website using real world audio. So audio actually just recorded from like a YouTube video. And we have one where it works reasonably well there also. But just for demonstration, I use this one because it's a little more clear to see what's going on. But just an important caveat, I don't want to, I gotta add the disclaimer. Cool. Question.
Is there a way to kind of determine how many sub-audios you have, like automatically?
Yes. So if you look on the future directions thing, that's the thing I was just going to mention, actually. That is an excellent question. We were already kind of thinking of that. Unfortunately, implementation-wise, it's a little bit more complicated to get that working. But yeah. What would be really cool is practically if you could use some sort of captioning model, or you could use some sort of audio to text model to basically try to transcribe what's going on in the video, and then use that information to automatically generate the prompts, and then use that to separate the sources, right? Yeah. And John even came up with a really clever idea to sort of do this even recursively. So you could keep kind of recursively subdividing the audio. It was a little outside of my experimental capability to implement that at this point, just because that requires, I don't know, patching like OpenAI Whisper and like some sort of captioning model into like an LLM, and then patching it back into this, and then having them all hopefully converge to something reasonable. But if you're better at programming than me, you might be able to get that sort of thing working.
Because the approach is kind of not limited to two audios, right?
No.
It's kind of, you're saying it's linear, so you can kind of technically have like any number of audios.
Absolutely, yeah. If you wanted to go nuts, you could record a flock of birds and go out there and count all the birds individually and separate the 512 birds or whatever.
Yeah. Cool.
Birds always come in powers of two. Okay, what else have I got left here to say? Just to be clear on the limitations, I already talked about the synthetic data thing, but also, we had a lot of failure cases. The really key thing here is that since you're relying on a pretrained diffusion model, you're going to inherit all the biases and all the blind spots in that diffusion model. So an obvious thing here is that we're dealing with music. This is trained on primarily Western music. So if you tried to generate, say, music that uses like a different scale, it's like something that's not like 12 tones, it's not used so much in the West, it would struggle with that. It would struggle with pretty much anything that's not in the training data in some sense. Of course, it's interpolating. There is some sort of advantage to doing this because you're leveraging the sort of features that are extracted from the data set. But if there's some huge blind spot in that training data, it's not going to be able to fit the parameters you're trying to optimize to something in that area, right? So you just have to understand that if you're using one of these sort of distillation methods, right? Yeah, and kind of preempted the future direction there. It's a great question. Yeah, I guess in the future we also kind of want to look at. It would be cool to look at some more synthesis methods, to do some kind of more robust kind of, I guess, ablations on what we've run. Spatial audio is another thing we thought would be really cool, but practically was kind of a nightmare to reason about. So if you could have different sources over space and use this to sort of optimize, the spatial positioning of sound, because for human beings, that's obviously a huge part of how we kind of tell what's going on in different spaces and, reason about the environment around us. So yeah, trying to explore some of those avenues would be great. Is there a question in the chat?
Someone was asking what model we used for the source separation.
Yeah, so it's all the in this paper was done with stable audio open, because that was pretty much the first open source like audio diffusion model that was really kind of doing things to a level of quality that made these starts possible. You could definitely use other ones. That's kind of what's neat about this is it's a general method. It's agnostic to what's going on inside the diffusion model itself. So you can drop in another one and see. We just happen to use that one because it came out right when we started the project.